My name is Gautam from Sadavarte, Assistant Professor in the Department of Chemistry and the Applied System Science and the Commerce College, Charleston. Now we are starting lecture series on spectroscopy. The spectroscopy consists of 3 to 4 lectures on spectroscopy. There are 4 types of organic spectroscopy. First one is a UV visible, ultraviolet and visible spectroscopy. Second one is IR. Third one is NMR. And last one, now that is a mass spectroscopy. So before starting, we must know what is a spectroscopy. What is a spectroscopy? Spectroscopy means the study of interactions between electromagnetic radiation and matter. So I think all of you know very well matter. So anything exists in nature which have a definite, which have a shape, volumes, which occupy space. So that is called matter. When electromagnetic radiation falls on that matter, some interaction takes place with that matter. And now that interaction is to be studied in a spectroscopy. So this spectroscopy are of 2 types basically. One is absorption spectroscopy and second one is emission spectroscopy. Now all of you know very well light made up of various types of radiations. And in that some portion of light, that is the electromagnetic radiation, we can take. So this is a wave. Wave is associated with a spectroscope. So this is 1 terms. Wavelength, amplitude. We will see one by one. So these are some various parameters. So what is a waves? So I think when this wave is to be there. Now, so what happened here? Now when this wave transfer, now what happened here? Now that passes or it is a perpendicular to this axis. So there is a one distance. Now that is a maximum. And second one is a minimum. So this maxima, they are called as a crust. So these are maxima which has to be shown here. Now these are maxima. These are 2 maxima which are here and this is a 1 minimum. So maximum they are called crust. So the distance between 2 successive crusts. The distance between 2 successive crusts or 2 successive trough. Now they are called as a wavelength. And this wavelength is a denoted by means of lambda. Generally, wavelength it is a measure in the form of nanometer. Or this is the maximum distance from the point of propagation. No, they are called as an amplitude. So this is amplitude. So we want to discuss these are various points. Now in that frequency. So what is the frequency? It is the number of waves or number of cycle which pass to a fixed point in a per second or per unit time. So they are called as a frequency. And frequency denoted by means of a nu. Second definition, it is a amplitude. Now just I have to view that the maximum length of electric vector in the form of wave from the x-axis. That is a maximum height of the waves. So whatever that maximum height of waves. So see this is a wave and this one is a maximum height. Now these are called as a what we can say, now that is nothing but amplitude, and amplitude it is denoted by means of a A. Now next one is a wavelength. So what is a wavelength? It is a distance between two successive crests or trough are called as a wavelength, and wavelength it is a denoted by means of a signal, it is a denoted by means of a sign. Now that is nothing but lambda. And last one is a wave number. Wave number it is a reciprocal, or it is a number of waves per centimeter unit. Or it is a reciprocal to that of the wavelength 1 by lambda. Now that is nothing but a wave number. So what is the energy? So I think all of you know very well electromagnetic radiations. So this electromagnetic radiations, it is in the form of discrete particles or wave packet. Now, and this packet, small packet consists of a energy, and now that energy they are called as a photons. We can relate this energy of a photon to its wavelength and frequency and wave number by means of a given equation. Now there is a one equation, E is equal to h nu, where E is a energy, h is a Planck constant, and nu is a frequency. If nu, it is a nu, what is that? Nu, it is the nu, it is a C by lambda, where C is a frequency, C is a velocity of light, and lambda is a wavelength. So again, it is to be given here hc nu, where h is a Planck constant and its value is a 6.63 into 10 to the power minus 34. And this is the energy, E is equal to h nu, or hc by lambda, or hc nu. It is a very important equation on basically this equation. Some problem it may be asked at the UC level as well as the PC level. So in this case, energy is to be calculated where wavelength is to be given here. So in that, you know energy, so you know Planck constant, you know the velocity of light, or if you know the wavelength, then you are able to calculate the energy of electromagnetic radiations. So this energy is inversely proportional to that of the wavelength. See here, this is E is inversely proportional to the wavelength. Okay, so this is a very, and I think all of you know very well what is the electromagnetic spectrum. So electromagnetic spectrum, it is arranging the whatever that arranging the radiation according to increase in a wavelength. See from left to right. So this is a gamma rays now that are very very small wavelength, and this one is a last one now that is nothing but a radio frequency. The right side now that consists of radio waves, and now that is a longer wavelength. So when they are arranged according to increase in a wavelength, now they are called as a what we can say electromagnetic spectrum. So this electromagnetic spectrum consists of gamma rays. Now that having the wavelength it is up to 10 to the power minus 2 nanometers. So this is X-rays. Now X-ray it is a 10 to the power minus 2 to 10 to the power 0. So this is a wavelength of what we can say X-rays. Now this if you see the gamma rays, now that have a smaller wavelength, and it means that it have a larger amount of energy, much more of energy. This one is a gamma rays. X-rays now that have a lower to that of the gamma rays. Now next one is ultraviolet. Ultraviolet it is a 10 to the power what we can say for 200 to 400 nanometers. So it is a given here 200 to 400 nanometers ultraviolet, and visible it is a 400 to 800 nanometers. So this is ultraviolet, and this one is a visible. Now after that, next one is a infrared radiation. So that infrared it is nearly about 10 to the power what we can say 10 to the power 4. So this is infrared. Again it is to be given here in the form of nanometers. So in the form of microns, generally it is I think 0.5 to 200 microns. So this one is infrared. Now, in case of ultraviolet visible spectroscopy, in that case, electronic excitation is to take place. And in case of infrared, now the molecule undergoes stretching as well as a bending vibrations. So these are various types of vibrations, stretching vibrations as well as a bending vibrations, symmetric stretching, asymmetric stretching, etc., etc. Later on microwave, this is again microwave radiation, so it is associated with another type of microwave spectroscopy. And last one, now that is nothing but radio frequency. So in that case, now the wavelength, it is from 1 centimeter to up to the hundreds meter. So whatever that wavelength, now that is in the form of meter, it is to be given. And this one is a visible vision. So this is a UV ultraviolet, 200 to 400 nanometers and 400 to 800 nanometers. Now that is nothing but a visible vision. So UV 180. In some book, it is given as a 200 to 400 nanometers. And visible 380 to 780 nanometers. Now, these are some types of spectroscopy. What type of interaction takes place in that molecule? Now, that is to be clear. Ultraviolet visible spectroscopy. Now, that is a UV region. Now, in that case, bonding electrons. So, whatever the electrons which are there, now that electronic excitation is to be takes place. Now, second one is atomic absorption spectroscopy. It is also offered in a UV visible spectroscopy. In that case, atomic transition. So, that valence electron. So, if you see the sodium, its electronic configuration, if you see, after most orbit consists of only one valence electron. So, that is responsible for electronic atomic absorption spectroscopy. Next one is the FTIR. Fourier transform infrared spectroscopy. In that case, IR, infrared radiation. Now it undergoes vibration as well as rotations. Now, in that case, various types of molecule undergo vibrate. Similarly, that molecule also undergo rotations. Now, next one is a Raman spectroscopy. It is also inorganic spectroscopy. Now, it is that is occur in infrared radiation. In that case also, now it undergo vibrations. Now, next one is a NMR. NMR means nuclear magnetic resonance. In that case, now whatever that radio waves in the form of meters. Now, in that case, the nuclei which are NMR active, now that only undergo what we can say nuclear magnetic resonance. Now, these are different types of spectroscopy. UV visible spectroscopy. In that case, electronic excitations. It is to be occur. So, this one is electronic excitation. Later on, fluorescence. Fluorescence means, I think all of you know fluorescence and phosphorescence. So, what happened here? Now, the electrons which are to be there, now that absorb the energy. So, whatever that atom which is to be there, now that absorb energy. And when, what happened? Now, it goes in an excited state. And when that in an excited state to ground state, what happened? Some energy is to be emitted. And now that energy emitted in the form of fluorescence. So this is another one. Now that is talking about fluorescence. FTR, now that is IR. In that case, vibrational transition of a molecule. Now that molecule undergoes vibrating. So these are stretching vibration as well as a bending vibration. Again, these stretching vibration are of two types. Again, bending vibration are of two types. Then we will see IR, we will see in detail. Later on, NMR, nuclear magnetic resonance. In that case, nuclei. Now that nuclei undergo spin. X-ray spectroscopy. Now this is it is a relative, right? It's associated with the crystal structures. In that case, also electronic excitations it is to be occur. Now, in case of the energy band in a molecular absorption spectroscopy, it is some of a different three types of a component. Now, that is a electronic, vibrational, as well as a rotational. So, due to that, what happened here? Now, the transitions between the electronic, vibrational, rotational, it gives rise to a band. And that band, it is appear, now that is a broad band. In this case, now whatever the Lambert-Beer law. So this is associated with the visible spectroscopy. So this is a source of light. When this is a source of light, it is a passes through sleep. So what happened here? we can select a specific light. And when this light, it is a passes to the sample. This sample, it is a cuvette containing sample. So what happen here? Now, some radiation, it may be absorbed, some it may be transmitted, or some it may be reflected. So whatever that, some is absorbed and some is to be transmitted. So whatever that, the fraction of incident light absorbed is directly proportional to the number of absorbing molecule in a path. So that is a Lambert-Beer law. So what is the Lambert-Beer law? It is a decrease in intensity of incident light, decrease in intensity of incident light is directly proportional to the concentration of solution as well as a path length. So what is that? Path length of that solution. This equation, it is log of I0 upon I is equal to epsilon LC. Where epsilon is a constant, L is a path length, and C is a concentration of that a particular solution. Where I is the intensity of incident light, I is I0. I is the incident intensity of transmitted light, and C is the concentration of sample, and L is the time of a sample. So, and this is epsilon is a molar absorptivity constant. So, as also fixed in value. So, this is a given sort of Lambert-Beer law. So, there are various sources of sample sources of light. It is to use ultraviolet visible, in that case quartz. Fused silica, now they are used as a sample holder, and in that case deuterium lamp, no, they are used as a light source. And detector, now that is not a phototube. Next one is a visible, in that case our tungsten lamp, now they are used light source. Glass or quartz, now that is a sample holder or sample tube. And phototube or diode array, now they are used as a detector. Next one is infrared. In that case, now there are whatever that rare earth oxide or silicon carbide, now they are used as a light source. And whatever that salt of crystal, now that is in that case generally sample holder, what we can say so. And thermocouple tube, now they are used as a detector. So these are electronic excitation that is to be occur. Now there are four types of electronic excitation. First one is a sigma to sigma star. See, this one is a sigma. So these are various energy levels. Sigma bonding, pi bonding. This one is N for non-bonding energy level. Pi star. This is a pi is a bonding, and pi star is anti-bonding. Sigma is bonding and sigma star is a anti-bonding. So these are basically four types of electronic excitation. So this is a sigma to sigma star. Now that requires a very high amount of energy for this process. So it occur only and only in alkane. So whatever that transition which are occur, now this transition, it is to be occur in alkane only. Not only alkane, but just alkane content. Those compound or those structure which contains sigma bond, now that undergo what we can say sigma to sigma star. Generally, basically alkanes. All alkane undergoes sigma to sigma star transition. Now next one is a pi to pi star. Now the compound which contain a pi bond, those compound, जो भी कंपाउंड है जिसमें भी पाई बॉन्ड होता है वो जो है वो पाई टू पाई स्टार ट्रांजिशंस इट इज टू बी ऑकर. Example, carbonyl compound C double bond O as well as C double bond C. What are that alkenes as well as a carbonyl compound, now that also undergo this type of excitations. Now that is nothing with a pi to pi star. Next one is a N to sigma star. Now the compound which contain sigma bond as well as a non-bonded pair of electrons. Here OH, oxygen. Oxygen contain sigma bond as well as a non-bonded pair of electrons. Now generally alcohol undergo what we can say N2 sigma star. And last one is the N2 pi star. Whatever that the carbonyl compound also undergo this type of N2 pi star. So whatever that N2 pi star. N means non-bonded and pi means pi bond. So carbonyl compound contain non-bonded pair of electron as well as a pi bond. Let's see. So it undergo what we can say pi to pi star excitation. So this is basically this questions it may be asked. So this is a very important questions. Normally it is asked in a spectroscopy. Now next terminology in a UV visible spectroscopy. Now that is nothing but a chromophore. So what is a chromophore? Chromophore is an unsaturated group. It contains carbon-carbon double bond, carbon-oxygen double bond, carbon-nitrogen double bond. Now carbon-carbon double bond, carbon-oxygen double bond, carbon-nitrogen double bond, or carbon-nitrogen triple bond also. So these are unsaturated. Now they are called as a what we can say chromophore. Now it is in between 100 to 400 nanometers. So see, this is a benzene. Benzene, if you see benzene, it is a colorless. It shows just absorption at about 200. But when this is ethylene, another, it shows at about 170 nanometers. Now, second one is oxochrome. Oxochrome, it is a saturated group. So this another previous chrome 4, it is an unsaturated. Now, oxochrome, this is a saturated group which does not absorb UV radiation at a longer wavelength. But when it is connected to chromophore, see, simple. If you see OH, it does not absorb anything. But when it is connected to benzene ring, or when it is connected to the compound which contain a carbon-carbon double bond, it is connected to conjugated system. So let's change its both wavelength as well as its intensity. For example, it is to be given here OH, NH2, and Cl. See, this one is a benzene. It shows a absorption at about 255. But when this benzene, if it is to be connected to OH group, so what happened here? When it is connected to OH group, so what happened here? Now its intensity, it goes on a increasing. So whatever that this इसकी जो भी intensity जो है, so whatever that wavelength जो है, so there is a increase in a wavelength. If you see aniline, when it is connected to NH2 group, so what happened here? Again, it is to increase. Now at about 280 nanometer. Now next, there are two types of shift: bathochromic shift and exochromic shift. So the shift in absorption to the longer wavelength. Shift in absorption to the longer wavelength. See here, it's example. It is also called as a red shift. See, in this case, what happened here? Now wavelength goes on increasing. See its example. If you see the phenol show the radiation at about its wavelength at about 270 nanometer. So it shows a wavelength at about its absorb at about 270. But 70. If you remove the OH group, in that, if you remove the hydrogen, so what happened here? Phenoxide ion. So what happened here? Now its intensity, it's what we can say, its wavelength goes on increasing at about 287 nanometers. So these are called as a red shifts. Another example, phenol, para-nitrophenol. It is at about 320. But if you see its phenoxide, पैरानाइट्रोफेनॉल का अगर आपने फेनॉक्साइड लिया तो सो व्हाट हैपन हियर सो इट शोज its wavelength goes on increasing at about 400 nanometer. Next one is exochromic shift. अभी ये इसके अपोजिट में होगा. ओके है मतलब बाथोक्रोमिक शिफ्ट जो है इसके अपोजिट में होगा. सो व्हाट इज अ hypsochromic shift? Shift in absorption to the longer wavelength, shorter. अभी पहले जो हमने क्या देखा था टुवर्ड्स व्हाट वी कैन से लॉन्गर. अभी क्या होगा? शॉर्टर होगा. शिफ्ट इन एब्सॉर्प्शन टू द शॉर्टर वेवलेंथ. नो दे आर कॉल्ड एज hypsochromic shift. It is also called as a blue shift. So In this case, lambda max value goes on increasing. If you see the aniline, aniline shows absorption at about 280 nanometers. But if you mix this aniline with the HCl, now what happened here? So it gets converted into aniline hydrochloride. So what happened here? Now it's a wavelength goes on decreasing. So it is in aniline 280 and in aniline hydrochloride 203 nanometers. Now there are some rules for a calculation of lambda max value of a lambda max value of alpha beta unsaturated compound. So these are some these are so very okay. Now we will see a remaining portion in the next lecture. Okay. Okay. Woodward Fisher rules we will see in the next lecture.